Hi everybody, I here will show you the result coming from this overview paper that is now under review. That is actually the part 2 of what Jesus has just now presented, where we do a comparison of 3-kilometer convection permitting simulations with high resolution observation and an ensemble of coarser simulation that drives the 3 kilometers one over the alpine domain. And we will look to results for precipitations and indexes related. This is the list of the models that are in the ensemble. And you see started the EUCP models members. The other belongs to flagship of Eurocordex. So we have 12 simulation in total, and you see on the right the strategy, the nesting strategy that we have used, with the only exception of UK Met Office that has not an intermediate domain. The observation that we are using for the analysis covers almost all the domain, are high resolution going from kilometer scale to some kilometer, and in some cases we have hourly data available overlapping the period we are interested in. So here I show some results that is in line with what Jesus has just now presented for the ERA interim simulations. You see here the summer season and the fall season for the daily precipitation across the historical period. And from top to bottom, you see mean precipitation, wet day intensity, wet day frequency, and EV precipitation represented with percentile 99 precipitation. So you see the observation on the left and the high and low resolution middle and right panels of each figure. So you can see that we found that biases are generally reduced when we use a high resolution ensemble. And in particular for the summer season, we see that improvements on the mean precipitation are due actually on improvements for frequency and intensity at the same time that corrects somehow the deficiency of the coarser resolution ensemble that produce much more overestimated frequency events and too low intensity event during the day. Also, a comment here, very positive, is for EV precipitation. In fact, you can see that for both summer, but mainly for the fall season, on the last row, you can see that using a high resolution ensemble allows us to improve a lot the simulation of EV precipitation events, and in particular over some area that is besides the alpine one. I mean, some area around the Western Mediterranean that during fall season is particularly interested by severe events that usually hit these areas. So, of course, these are the ensemble mean. We have large spread among all the members of the ensemble. This is mainly true for the summer season. For the other season, we have, let's say, the members are more in line among them. For summer season, we see the largest spread among the model, and I've reported here the mean daily precipitation as an example. The same comparison has been performed for the hourly precipitation. You see that the convection permitting ensemble recovers somehow the underestimation of the 12 kilometers ensemble for the intensity, and reduces the bias for overestimated wet frequency, especially around the orography for both seasons. And again, you see the improvements for the simulation of EV precipitation events around both orography for summer season and also around the Western Mediterranean for the EV precipitation that is here represented through 99.9% precipitation percentile. So if we have a look to day cycle, summer day cycle for each index, you see here in black the observation, and red and blue the high and low resolution ensembles, and you see also the single models on each figure. You see the spread is very large, but if we look at the ensemble mean for each indices, we see that switching to explicit representation of convection allows to recover somehow the deficiency of driving models ensemble in producing too often too low intensity precipitation. And also, as Jesus has already shown, a correction of the early onset of the diurnal convection is reached using the high resolution. Finally, for the evaluation period, we see here the probability distribution functions, and we see that over Italy and France for daily and hourly precipitation, top and down. You can see that the intermediate 12 kilometers model ensemble underestimated the daily precipitation for most threshold and misses the extremes. On the other hand, the convection permitting ensemble is able to cover the spread of the observation curve, but produces longer tails, two longer tails. So now, having all this in mind, we can go to have a look to daily precipitation change over the decade, going from 2009 to 2099. And again, the same indices are shown for summer and fall season. You see that in general, the 3 kilometers ensemble that is on the left for each figure tends to intensificate the magnitude of the signal where the two ensembles are coherent among them, between them. And the main difference in the summer season is for the intensity field on the cycle road we see here. The 3 kilometers ensemble, in fact, produce an almost everywhere positive signal, in contrast with the negative to positive going from south to north signal that we see for the 12 kilometers ensemble. And this is the main difference that we find between the two ensembles. And this is a modification of the sign change for this season. And this is particularly interesting for the signal that we see over the Western Mediterranean and over the Adriatic. Also, for what concerns the EV precipitation, we see that the two, for each season, the two ensembles are coherent. Besides, we see an intensification of the signal when we look at the high resolution ensemble. And also for the fall season, we see, even if over a smaller area around the Western Alps, we see a modification of the change signal going from negative to positive from 12 to 3 kilometers ensemble. So the same comparison is done for the hourly precipitation. Here the two ensembles are more coherent. We see again that the high resolution ensemble intensify all the signal that we already see on the coarse resolution ensemble. In particular for the EV precipitation index is here represented through percentile 99.9, we see an intensification of event during summer season over the alpine area. And I mean, going from 12 to 3 kilometers ensemble, and the same, but across all over the domain is true for the fall season. And if we look at the diurnal cycle, here you see again in red and blue, you see the 3 and 12 kilometers ensemble, and you can see with solid line the future period and with dashed line the historical reference period. You see that the two ensembles show coherent change signal between historical and projection simulation. The changes are actually bigger for the convection permitting, especially around the peaks, and except for the wet frequency that is reported on this panel for 3 regions, Switzerland, France, and Italy. And it is worth to note for percentile 99.9 that very heavy precipitation events here are indicated to decrease over Italy and France, to increase over Switzerland, and in particular over France. If we look at 12 and 3 kilometers ensemble, we see that there is also a switch of the sign indicating a decrease of this kind of event over France area. So finally, if we look at the distribution functions, we see that the PDF show changes for both daily and hourly precipitation. Here, the lighter colors are the historical period, and the darker color are for the future period. And again, blue and red is referred to low and high resolution ensemble. And we see that the 12 kilometers models ensemble shows small changes respect to the convection permitting ensemble. And this is mainly for increasing threshold. For the convection permitting ensemble, we see a large positive change, and especially for threshold going from high to extreme precipitation. So concluding, I don't recap everything that we have slide by slide said, but I want to remark that besides we are aware of a large spread existing among each ensemble member, here I was seeing that an ensemble-based approach has a lot of potentiality when we move to the kilometer scale. This kind of approach can preserve us by possible misleading conclusion drawn by single model approach, and this can be a strong benchmark when we go to analyze future time slice and climate change signals. Of course, now we need to move with to further more in-depth study, especially related to let's say to physically processes, to understand if these results are reasonable and if we are going on the right direction with an improvement using the high resolution. So that's all. Thank you.
Thank you. Thank you very much. Do we have any questions? Paula, hands up on the...
No.
No? Okay. So...
Sorry, we have a question from here. I couldn't raise my hand. I don't know how to do it. This is Ségolène and Lizzie. Do you have...
Yeah, can you hear us?
Only just.
Okay, I have a question. Thank you very much. It's nice to see the results coming out, and they show quite similarities to what we've seen here at some of the studies we've done here at the Met Office. I wondered if you've got some thoughts about trying to look at how significant some of the differences are, because you've got a lot of maps showing differences, the 3 kilometer and the 12 kilometer, but it would be nice to really use some approaches to actually identify where the differences really are significant, and then use that to home in your analysis, because I think in a lot of cases I'm not sure all the differences are indeed significant. Now that you've got 12 ensemble members, it'd be nice to use that information to look at that question.
Yes, we are going to go with, we are going to do more in-depth analysis, but I still don't have results ready. But we are good planning and going more in-depth with this point of view. I mean.
Yeah, and the other thing is, when you're looking at the extreme events for hourly precipitation, quite a lot of the work that we've done in the case of the 12 kilometer has shown that the differences are due to the fact you've got contamination with grid point storms, and that's something you might be able to look at a bit in your results. So often you can identify a grid point storm as having large amounts of convective and large-scale rainfall in 12 kilometre occurring at the same time. So it's quite a nice way to flag it. And when you're trying to understand the differences, you might find that's one of the reasons you're getting quite differences in the projections.
Yeah.
So, yeah, I also had a question about your PDFs, that's Ségolène from the Met Office, because you can see the tails of the PDF, they're kind of two tails in the red. If you can back to, is that WRF and Cosmo showing up?
Yes, I guess this group of models that are reported roughly with their own PDFs here, and these are, let's say, a group of models. They overlap and they sometimes produce this sort of double tail.
Yeah, so it's a more general question. It's how do we combine these two big ensembles of Cosmo and WRF with the single models like the UKMO and a few others? Do we give equal weight to every single realization?
Yeah, at the moment, yes, we consider each single model with the same weight, and we don't regroup our weight by group of models. But this might be a way to see something furtherly, but we have not done here.
Yeah, of course. Yeah, thank you. It was very interesting.